The impending slippage of flexible cable. Belts and ropes. Over sheaves and drums. Is important in the design of belt drives of all types. Band brakes. And hoisting rings. This figure provides a drum subjected to two belt tension T1 and T2. Consider this picture. In the part A, this part show a drum subjected to the two belt resistance T1 and T2 as shown in the picture. The torque M, also shown in the picture, necessary to prevent rotation. M. To prevent rotation, and a bearing reaction R. With M in the direction shown, T2 is greater than T1. The free body diagram of an element of the belt of length R d theta is shown in part B. This part R d theta is shown in part B of the figure. We analyze the force acting on this differential element by establishing the equilibrium of element in a manner similar to that used for other variable force problems. The free body diagram shows that if we have T here, dt plus T here, and a normal dn which goes to a friction force mu dn. The tension increases from T and the angle theta T plus dt. As I said, the normal force is a differential dn since it acts on a differential element of area. Likewise, the friction force, which must act on the belt in a direction to oppose slippage, is a differential and is mu dn for impending motion. Equilibrium in T direction gives us this relation. T plus cosinus dt un, so we can make a mu dn equals to dt. Since the cosine of differential quantity is unity in the limits, equilibrium in the n direction can be written as this relation. Equilibrium in n direction. In the n direction, for this, in the n direction, dn sinus plus t so dn also equals to t d theta, where we have used the fact that since of the differential angle is the limit equals to the angle, that the product of two differential must be negated in the limit compared with the first order differential remaining. Combining the two equations, equilibrium, the first one is, and the first one was dt. We have this relation, mu d theta, mu equals to dt on t d theta, or mu d theta dt on t. In making an integration from t1 to t2 dt on t 0 to beta, the beta is contacting angle. So we have this relation. Note that beta is the total angle of the belt contact and must be expressed in radians. If a rope were wrapped around a drum n times, the angle beta would be 10 2n pi radians. This equation holds equally well the non-circular section where the total angle of the contact is beta. This conclusion is evident from the fact that the radius r of the circular drums does not enter into the equation for equilibrium of the differential element of the belt. The relation expressed in this relation also applies to the belt drives where both the belt and the pulley are rotating at a constant speed. In this case, the equation describes the ratio of belt tension for the slippage or impending slippage. When the speed of rotation becomes large, the belt tends to leave the rim. So the equation 6.7 involves some error in this case.